Present speaker.
Hi.
Hi.
Okay, Atul, you can start the proceedings, I suppose.
Okay. Good afternoon again. So we are meeting here again for the second lecture by Professor Kaneenika Sinha from Mysore, Pune on central limit theorems in number theory. So over to you, Kaneenika.
Okay, thank you, everyone. So thank you to the organizers again for the opportunity to talk about central limit theorems in number theory. And thank you to all the audience who are here today. So a very quick recap of our last lecture. We had discussed central limit theorems in the context of this very beautiful function in number theory, namely the prime omega function. So this counts the number of distinct prime divisors of n, and we saw some nice properties of it. It is an additive function that's easy to see, and we saw how to evaluate the average order of omega of n. So this is telling us asymptotics about the mean value about the function omega of n, which leads to further more refined questions related to variance and higher moments, etc. So just one second. Yeah. So we learned the theorem of Hardy and Ramanujan, which gives us an upper bound between omega of n for the second moment of the difference between omega of n and its expected value. But actually something much sharper is true. In fact, instead of less than log x, we now know by the theorem of Erdős and Katz that this is in fact asymptotic to log x. And not just that, you can actually evaluate higher moments of omega of n minus log x normalized by square root of log x, and you end up getting the rth power moments of the Gaussian distribution. So this is the famous central limit theorem in number theory, the theorem of Erdős and Katz. And the perspective to prove this theorem is to actually interpret or compare omega of n in terms of sums of independent random variables. So here is a heuristic argument. Given a prime t less than or equal to x. So let us first consider the space of all natural numbers up to x and equip it with the uniform counting measure. And on this, define the random variable x sub p to be equal to 1 if p divides n and 0 otherwise. And intuitively, xp and xq appear to be mutually independent. So we model these variables in terms of Bernoulli random variables with similar properties and which are known to be mutually independent. And we then compare our expected value of xp's and variance with known probabilistic models. And the central limit theorem can be predicted by observing that the sums of xp's is what is your omega function. And therefore, you can talk about distribution of sums of independent random variables. These are, however, not identically distributed. So all the properties that we learned can be now interpreted in probabilistic language. And so a central limit theorem predicts the distribution of the sums of these random variables appropriately normalized. And this was proved rigorously by Erdős and Katz. So you can't quite apply the central limit theorem. You use it to make some guesses, and then you use explicit number theoretic methods to prove this distribution. And this leads to this nice theme of probabilistic methods in number theory. This is one probabilistic method, namely whenever you have a counting problem, for example, average order of an arithmetic function, then you express the arithmetic function as a sum of independent random variables. You guess their probabilistic distribution of normalized sums using central limit theorems, and then you prove the above rigorously. So for example, Erdős-Katz's theorem can be generalized to all additive functions. We saw some theorems last time about how one could try and generalize our knowledge of omega of n to general additive functions. But now we move over to different types of functions. So none of the sequences or functions that we consider today are going to be additive. So we'll be considering other types of sequences. So what we do is we consider finite families, okay, depending on the kind of things that we like to work with. Suppose we have some finite families which we equip with the uniform probability. For example, you could take families of certain types of curves over a fixed finite field. Let's call it F sub q. Okay, so your curves could be, say, elliptic curves or hyperelliptic curves or other types of model families of curves. I will give you some examples soon. And q is a prime power here, since we are talking about finite fields F sub q. Okay, another type of family, for those who are familiar with the notion of modular cusp forms, is to take positive integers k and n, where k is even, and consider the set of all Hecke nu forms lying in the space of modular cusp forms or weight k with respect to gamma naught of n. So this is our family. So the set of Hecke nu forms forms a basis of a certain subspace of your modular cusp forms. It's a finite dimensional vector space, and its basis is what the basis has some special properties. They are simultaneously eigenvectors of a class of operators called the Hecke operators, and we can consider this set of Hecke nu forms as our family. We know that there are finite, for a fixed k and n, there are finitely many elements in this set. Okay, another very interesting type of family that one could consider are families of d-regular graphs on n vertices. Okay, so I will be giving you detailed definitions, at least for the graph theory things quite soon. So here what we have is, we talk about eigenvalues of adjacency matrices of these graphs. And the questions that we ask pertain to distribution of families of these eigenvalues as you let n go to infinity with d fixed, or when you also allow d to grow along with n. So we are interested in the distribution of certain sequences that arise in each of these contexts. And the fundamental function that we want to consider when we are looking at counting functions is, for a fixed interval I, we want a counting function that counts the number of elements of your specific sequence lying in the interval I. Okay, and we try to interpret this counting function as a sum of seemingly independent random variables to be able to apply the probabilistic theme that we have studied so far. Okay, so these, as I said, they can be interpreted as sums of random variables. And so the question is, can we have central limit theorems for these counting functions as your size of the families goes to infinity? Okay, so the first situation that we go over is families of curves over finite fields. This will not be a very detailed description, but I will give you some main theorems in this field and then move over to the other families. But first of all, what is the motivation behind studying these types of families? So the motivation actually goes to the birth of the interface between random matrix theory and number theory. So the fundamental motivation goes back to a very nice work of Montgomery on what is called the pair correlation of zeros of the Riemann zeta function. I forgot to mention this in the slide, but there are also some very nice theorems of Selberg about central limit theorems for zeta zeros. So in the context of Montgomery's work, the main theme was the similarity between the statistics of zeros of L functions and statistics of eigenvalues of random matrices. Okay, so after Montgomery and Freeman-Dyson met and discussed their work, they realized that essentially they were looking at a common phenomenon, but Montgomery was going at it from the point of view of zeros of L functions, whereas Freeman-Dyson was looking at statistics of eigenvalues of certain types of random matrices. So Katz and Sarnak had this perspective of considering these statistics of zeros in families of L functions, so in suitable types of families. So it was natural to extend the study of zeta zeros of families to zeta zeros of families of curves over finite fields. In general, a lot of the zeta zeros of curves over finite fields, which I'll define shortly, are much better understood than zeta zeros of your Riemann zeta function or zeta functions in the Selberg class. And whenever you have analytic questions about Riemann zeta function or L functions, you invariably see that you can translate them into questions about zeta functions for curves over finite fields. And those questions are very well understood in this context. So the statistics of the zeta zeros can be modeled as sums of independent, identically distributed random variables. Okay, so brief introduction to zeta functions of curves. Let us take Q to be a prime power, and let C be a smooth projective curve of a certain genus G defined over F sub Q. For technical purposes, we will take Q to be odd. Okay, now this projective curve can be understood in terms of an affine plane model. So something, basically an equation in two variables, f of x, y equal to 0, where your f of x comma y is a suitable polynomial. So our examples, we can take y square equal to f of x, where f of x is a square-free monic polynomial over f sub q of degree 2g plus 2. Okay, and we can take all such polynomials f sub x, f of x, to give us a family of these curves, which are called hyperelliptic curves. Then you could consider other types of families. Another natural family to consider is the family with equation y to the L equal to f of x, where now your f of x is a monic polynomial and it is Lth power free. So generalization of square free to Lth powers. L is a suitable prime in terms of Q, and your f sub Q has a certain degree, which there is a formula in terms of your genus of this curve. Okay, so then you could consider families of this type. Okay, another interesting family is that of what are called Artenstrual curves. So here P is a prime, and in fact P is the characteristic of the field f sub Q over which we are defining these curves. And now the equation is y to the P minus y is equal to f of x. So here f of x is a polynomial of degree d, not divisible by P. So we can now consider families coming from equations of this form. And I'll later give you a theorem which sort of unifies these different examples. Okay, so given a smooth projective curve of genus G, which you have defined over f sub Q, let n sub n denote the number of points on C whose coefficients lie in an nth degree extension of f sub Q. Okay, and your zeta function can be defined in terms of these quantities. So the zeta function of C is over your field f sub Q is defined as the exponential of this infinite sum. And the amazing thing is, because of the arithmetic of function fields, you can see that your zeta function can be written as a rational function, where the numerator is a polynomial that depends on your curve C, and it is a polynomial of degree 2g, okay, such that its value at 0 is equal to 1. This numerator satisfies some kind of a functional equation that relates u to 1 over qu. So because of this, one guesses that the zeros of the zeta function z all lie on the circle absolute u equal to 1 over root q. Okay, so fortunately, the Riemann hypothesis for these zeta functions has been proved by Andre Weil. And because of this, now what you can do is you can write your numerator, PC of u, in terms of linear factors, okay, where all 1 minus u times alpha j of c, where absolute of alpha sub j of c is equal to root q. So now the question is, suppose I consider a family of curves. How is this set alpha sub j of c as you go from 1 to 2g distributed? Okay, so more precisely, because you know that the absolute value is equal to root q, you can write it as a complex number, root q times e raised to the 2 pi I theta j of c, where theta j of c are the corresponding angles for these zeros. They lie in the interval minus half to half. So the question that we ask is, how are these angles, theta j of c, distributed as we vary c over specific families of genus G curves? Okay, so we can consider this question in different perspectives. You could either take Q to be fixed and let your G go to infinity, so your size of families are still increasing, or you could take both G and Q to go to infinity. Okay, so the first early work was done for both G and Q going to infinity using relations with random matrix theory. Let me make these notions a little more precise. So what do I mean about counting function when I say a counting function? So let us take, so we've got this interval minus half to half, actually should be open at half. So let us take any interval and let's take a symmetric interval about the origin. Let's label it as minus beta over 2 to beta over 2. And it lies inside this interval where all the zeros lie. And given this fixed interval, let n sub I of c denote the number of your j's or the number of angles theta j which lie in this interval I. Okay, so now what we do is we will fix interval I and study these quantities. So suppose just as while we were looking at the omega function, we talked about average order. Okay, here also we talk about the average value of this counting function as we vary C over our favorite families of curves. Okay, and we will be in situations where this average value of the counting function would be asymptotic to 2g times the length of I as your families grow in size. Suppose this happens. Then you can ask finer questions about error terms in this asymptotic, and you can also ask questions about the second moment, that is the variance, or higher power moments of the difference between these. So we would like to study the fluctuations of n sub I of c minus this expected value 2g times length of I as we vary our curves in our families. So again, we had introduced the family of hyperelliptic curves of genus G. So these are curves of the form y square equal to q of x, where q of x is suitable polynomial of degree 2g plus 2. So one very nice theorem in this context is by Katz and Sarnak, who show that if you let your field go to infinity, okay, the statistics of your zeta zeros start to match the statistics of eigenvalues of random 2g by 2g special types of matrices over F sub q, which are the unitary symplectic matrix. We need not go too much in detail about the random matrix side, but this is just to give you an idea of the relationship between zeta zeros of curves and zeros of random matrices over finite fields. Because of the work of Katz and Sarnak, we actually have an asymptotic form of the central limit theorem. So if you vary your curves over this family of hyperelliptic curves, okay, then you have estimates for the variance, and then you can normalize by the square root of the variance, take the limit first as q goes to infinity, then take the limit as g goes to infinity, meaning the size of your families is also increasing. Then these limits actually converge to the rth power moments of the Gaussian distribution, which is what we also had for the omega function. So there seems to be some underlying similarity there, even though these are vastly different. They look like vastly different families. So now, of course, here the question is, as I had mentioned, we can also ask questions about what happens if you fix Q and let your size of the families of curves go to infinity. So this question was considered by Dmitry Feifman and Zev Rudnick. They considered this distribution for a fixed f sub q, and they proved the following. Okay, let us state their theorem. Let I be a fixed interval in minus half to half of the form that I mentioned to you before, a symmetric interval. Actually, in general, you don't necessarily have to take a symmetric interval, but the calculations are nice to write in this way. But the main thing is it's a fixed interval. As g goes to infinity, the expected value of the counting function, which counts the number of zeta zeros lying in the angles corresponding to zeta zeros lying in the interval I, this is asymptotic to 2g times the length of I. So we have asymptotics for the expected value of n sub I. So the next question is about variance. So they also obtain variance for these families. And the variance in this context turns out to be asymptotic to 2 over pi square log of 2g times the length of I. Okay, so see, this looks very, very different from the situation of our prime omega function, but the kind of questions that we are asking are very similar. Okay, so the general form of the theorems is quite similar. And as in the case of the Erdős-Katz theorem, if you take the rth power moments of these variables that you construct from n sub I of c, you end up getting that they are asymptotic as g goes to infinity to the rth power moments of our Gaussian distribution again. So this was the theorem of Feifman and Rudnick. Mao-Sheng Xiong in the same year, he generalized the theorem of Feifman and Rudnick to another type of families, which I had also mentioned before, families of curves of the form y to the L is equal to f of x. Okay, and then a similar kind of a theorem can also be obtained for the other family that I had mentioned to you, namely the Artenstrual curves. So these are defined in terms of the equation y to the p minus y equal to f of x. And as the f varies over certain conditions, we have our appropriate family of Artenstrual curves. And we have an analog of the central limit theorem for zeta zeros for hyperelliptic curves and the L-fold covers for these families of curves as well. So this is joint work with Alina Bukur, Chantal David, Brooke Fagan, and Mathilde Lalline. So now, of course, the question arises whether we just choose our families, is there a general theme behind choosing our family of curves? So we ask questions about common patterns, and the answer is yes to a large extent. So let us take f sub. So this is a little technical, but I do want to give you a brief overview of that general pattern. So let us take a rational function field over let k be equal to f sub q of x, be the rational function field over f sub q. You can interpret various types of families of curves in terms of field extensions of this rational function field. So the hyperelliptic curves correspond to quadratic extensions of your K with Galois group Z by 2Z. The L-fold covers correspond to extensions of K with Galois group Z by LZ. And the Artenstrual curves correspond to extensions of K with Galois group Z by PZ, where P is the characteristic of your field. So now the zeta function of a curve can be studied again in terms of zeta function of its function field. Okay, they are the same quantity, but they can be approached from these different points of views. And the previous results can be viewed as results for zeta functions of function fields okay, running over certain abelian extensions of K with specific Galois groups in different cases, which are isomorphic to Z by 2Z, Z by LZ, and Z by PZ, P being the characteristic of the field, respectively. So this leads to a general question whether we can actually restate all the previous theorems in terms of zeta zeros as we run over abelian extensions of our function field f sub q of x with a certain finite Galois group. Okay, so this is what Maosheng Xiong proved in 2015. It's a very, very beautiful, more general theorem. So without worrying too much about technicalities, I hope at least you will be able to see this general pattern here. So let K be as before, f sub q of x, and let G be a finite abelian group of some order kappa, such that your Q is congruent to 1 mod the exponent of G. Exponent of G is the LCM of the orders of all elements of your group. So let K be a Galois extension of K with Galois group isomorphic to G. So we consider all such Galois extensions, and let C of K denote the conductor of our field K over little k. So these are notions from algebraic number theory. We don't go too much into it. Okay, but basically in terms of these Galois extensions with certain finite, with a given Galois group, you can talk about families of extensions which have that, and then express your central limit theorem in terms of these families. So here our families become those finite extensions K whose conductor is equal to D, which was related to the genus of your specific curves. So this is a general formulation of the theorems that we saw before. Now, there are these very nice notes on arithmetic of function fields by Chantal David, where she describes everything from scratch, the motivation behind all these results, and state of the art with respect to different types of families, along with connections with random matrix theory. And I will share a link to those notes with you. They are available online. So, concluding remarks about this family. So I didn't quite show you how the counting function can be written as sums of certain types of random variables. That's because of the technicalities involved. And I just wanted to give you a brief overview. So this is explained in detail in Chantal's notes. The zeta function of a curve can be decomposed into a product of L functions corresponding to the characters of your group G, and n sub I of C is asymptotically a sum of independent and identically distributed Gaussian random variables, each of which is arising from a character of G, which I just mentioned above. And one little remark, Xiong's result does not cover the result about the Artenstrual curves because of the requirement of this congruence condition in his theorem. So there is something more happening in the Artenstrual family. And the above results can also be generalized to shrinking intervals. So we were taking an interval I and fixing it, but now we can also, as our families G go to infinity, we can also parametrize our intervals in such a way that their lengths become smaller and smaller, but in a controlled manner. The length of I may be going to 0, but 2G times length of I must go to infinity. So this is another generalization of the central limit theorems here. Okay, now let me just make some remarks about distribution of families, okay, or what is called equidistribution. So let us take omega to be a closed interval in R equipped with some probability measure mu. Okay, what we do is we consider families or finite sets lying in omega such that the cardinality of A sub V goes to infinity as V increases. Okay, so we've got this collection of families which are parametrized by V, and they keep increasing as you vary your V. Let us denote since your omega is a closed interval in R, let us consider the set of all continuous functions on omega. Say all continuous real valued functions on omega. Okay. Any questions so far? Sorry. Hello? Okay, I'll continue. For an interval I in omega, let n sub I of v denote the counting function corresponding to a sub v. So what is the number of t in your family a sub v which lies in this fixed interval I? So this is a generalization of the counting function that we saw for zeta zeros before. So we could have different types of families where we can define these counting functions. And we say that these families are equidistributed with respect to the probability measure mu if for any interval I in omega, the proportion of elements of your family A sub v that lie in the interval I is asymptotic to the measure of the interval I with respect to your measure mu. Okay, so in the context of zeta zeros, we were considering families where mu was equal to 1. Okay, so those families were uniformly distributed, but we can also talk about mu equidistribution for more general probability measures mu. And this counting function, asymptotic, is also equivalent to an asymptotic involving sort of the average value of your function over elements in your family A sub v. So the average value of f for lambda lying in A sub v is asymptotic to the integral of f with respect to mu for every f which is continuous on omega. So these two are equivalent conditions which tell us that your families are equidistributed over with respect to the measure mu. Okay, now one little observation. I think the PhD students may have probably studied or are studying this theorem in analysis, that you can approximate any continuous function on C of omega by suitable polynomials. Okay, so if you want to prove so this is basically what I'm referring to is the Weierstrass approximation theorem. And because of that, if we want to prove equidistribution, we don't really have to prove it for every continuous function. It will be sufficient to prove it for a sequence of polynomials of where p sub n of t denotes a polynomial of degree n. And let us choose a sequence of polynomials of each degree. So if you want to show that your families A sub v are mu equidistributed, then you just need to show that the average value of p sub n as you run over lambda in A sub v is asymptotic to the integral of your p sub n with respect to the measure mu. Okay, so a natural family to consider, at least in the other contexts that we will look at, are the Chebyshev polynomials. So what are Chebyshev polynomials? We are referring to Chebyshev polynomials of the second kind, so to speak. So these are given as follows. Suppose you have y to be equal to 2 cosine pi theta, then the nth Chebyshev polynomial is defined as sine of n plus 1 pi theta over sine pi theta. When you expand this expression in terms of 2 cosine pi theta, you will get polynomials in 2 cosine pi theta, and they are of degree n. In fact, we also have a precise formula for these nth degree polynomials, and we will see why we have chosen these types of families soon. Okay, so now a brief review of the other types of families that we want to look at, namely families arising from modular cusp forms. So this is our notation. Let k and n be positive integers, okay, with k even. Just 1 second. And let S sub k of n denote the space of primitive cusp forms of weight k with respect to gamma naught of n. let little sk of n denote the dimension of this space. So these are finite dimensional vector spaces over the field of complex numbers. And we know dimension formulas for these. And we also know that these dimensions grow to infinity if either the weight k or the level n or both go to infinity. Okay. So on these spaces, let T sub little n denote the nth Hecker operator. So we will be interested in eigenvalues of T sub n acting on these spaces S sub k of n. So there are some very well-known theorems about eigenvalues of these Hecker operators. So by the Ramanujan-Deligne bound, for a prime P, which is co-prime to the level n, the eigenvalues of P sub P lie in this interval. So if you were to normalize your eigenvalue T sub P by P raised to the k minus 1 over 2, your eigenvalues of the normalized Hecker operator would lie in the interval minus 2 to 2, irrespective of what your prime is. Okay. So the question that arises is, how are these eigenvalues distributed in the interval minus 2 to 2? If you let, for example, your spaces of cusp forms become larger and larger. So we denote the set of, first of all, we denote the set of Hecker new forms in Sk of n by f sub k of n. So this is an eigenbasis. This is a basis of this space of primitive cusp forms. And each cusp form in this basis turns out to be an eigenvector of all the Hecker operators. As a result, your Hecker new form, so this is actually, even if you don't know the theory of modular cusp forms very well, it is very important. The most fundamental facts we should remember is that these are finite dimensional vector spaces. Therefore, they have finite basis. We are considering special type of basis where the basis elements have Fourier expansions, and the nth Fourier coefficient is an eigenvalue of the normalized nth Hecker operator. So every question that we ask for these Fourier coefficients can be interpreted as a question about eigenvalue of these very special class of operators acting on these spaces. So we ask questions about distribution of Hecker eigenvalues, and we've got these analogs for distribution theorems in this space as follows. So this is a theorem due to Sarnak and Serre. So let A sub P denote the family of Hecker eigenvalues of Tp prime acting on Sk of n. Okay, we know that these lie in the interval minus 2 to 2. The question is, for a fixed interval I, how many of these eigenvalues would lie in the interval I? Okay, so we denote that counting function by n sub I and write it as a sum of the characteristic function of all the lambdas lying in A sub P with respect to the interval I. So the theorem of Sarnak and Serre says that if you let your families grow, families of your fk, this sk of n, if you let the dimensions of these families grow to infinity, then the proportion of these eigenvalues that lie in a fixed interval is asymptotic to the integral of a certain, it is asymptotic to the measure of the interval I, and the measure here is defined in terms of your prime P. This is what is called the p-adic Planteral measure. It is, so it depends on the prime P. Okay, so basically what we have is a family that seems to be equidistributed with respect to this measure nu sub P of T. So it is no longer uniformly distributed, as was the case for zeta functions of curves, but it is distributed with respect to another measure, which depends on the prime P. So now we try to model these questions in terms of sums of random variables. So let us choose an interval I lying in -2 to 2. And let us denote mu of I to be the measure of this interval I. For a prime P, which is coprime to the level n, define the following random variable y sub P, which takes the value 0 or 1. So y sub P of f is equal to 0 if a sub f of P does not lie in the interval I, and it is 1 if a sub f of P lies in the interval. Okay, so there is this, the famous Sato-Tate distribution theorem is essentially a theorem about distribution of sums of these random variables, which says that if you fix f in f sub k of n, okay, this sum of these random variables, y sub p, they converge to pi of x times mu of I as you let the number of primes go to infinity. Okay, and if you just look at a fixed prime P, this theorem of Sarnak and Serre that we just stated can be interpreted as theorems about the expected value of mu sub P. Okay, so this is known to be asymptotic to this mu sub P of the interval I. Then you can ask other questions about variance, and then you can ask if a central limit type of theorem holds for these YPs, for sums of these YPs. And it turns out in this case, if you wanted to find asymptotics for the variance, for example, okay, for a fixed prime P, this has not been done. It's quite, we don't seem to have the tools to do it. But if you sum over the primes P, then you have asymptotics for the variance for the sums of these random variables. Okay, so I would actually like to also go over to graph theory. So I will go over this quickly and basically give you a brief, let me just briefly mention the results. So as I mentioned, the sums of expected values of mu sub P can be shown to be asymptotic to pi of x times mu of I. So this is your analog of the fact that omega of n has normal order log x. This is the analog for this family. And then you can ask questions about variances. Fortunately, if you are summing over primes, okay, as long as your families are growing fast enough, you can find asymptotics for the variance of sums of the random variables y sub p. So this turns out to be asymptotic to pi of x times mu of I minus square of mu of I. This is joint work with my former PhD student, Neha Prabhu. And then you can also ask questions about higher moments. So we did that as well. So these sums of these random variables y sub p, when appropriately normalized, converge to the Gaussian distribution. So here is another analog of the Erdős-Katz theorem. And then you can talk about different types of analogs of these central limit theorems. Instead of the characteristic function, you can replace it by some suitable continuous function. For example, the mth Chebyshev function or linear combinations of different types of Chebyshev functions. Okay, so that work has also been done. Our motivation, I'd like to mention, was a 2006 result of Nagoshi, where he specifically considered the distribution of this particular sums of random variables. So he took a sub f of p to be his random variable, whereas we are taking chi sub I of a sub f of p. Okay, so so now let me, in the last few minutes, let me talk about a family which I think many of you may have studied in your combinatorics and graph theory classes. So we've got let me quickly introduce some basic notions. A graph, as we probably know, consists of a set of vertices and a set of edges between them. So suppose you have a set of vertices, okay? Let us take any two vertices, okay? And there could be an edge between them in your particular graph, or there may not be. So this is characterized by taking a certain subspace of V cross V. So any edge is characterized in terms of the vertices that it joins. So let Y equal to Vi comma Vj be an edge. We say that the origin of Y is Vi and the tail of your edge is Vj. Now, we will be in situations where our graph is undirected. Okay, if Vi, Vj lies in your set of edges, so does Vj comma Vi. Okay, so we don't really care what is the origin and what is the tail. So, a loop is an edge with the same endpoint. So if you have an edge which starts at Vi and comes back to Vi, it is called a loop. And a graph which does not have any loops and which is undirected is called a simple graph. So we are going to make our analysis quite simple. So we will take graphs which don't have any loops and which are undirected. Now the degree of a vertex refers to the number of vertices which have an edge from X, okay? And a graph is said to be a D-regular graph if every vertex has the same degree D. Okay, so I will come back to these notions later. So these are different types of objects inside graphs. So when you have a collection of edges, and you can talk about walks. So maybe there are two vertices which don't have a direct edge between them, but they can be joined by a combination of edges. So those notions are described in terms of walks and special types of walks. So the kind of walks that we are interested in are the following. So we are interested in walks which don't backtrack. So let's say you have a sequence of edges y sub I, your y2 should not go back on y1. Okay, so later on, let's say y5 could be the same as y1, but your y sub 2 immediately should not backtrack. So these are non-backtracking walks. And if you also have a non-backtracking walk where the last edge does not go over the first edge again, that is called a circuit. This term circuit is used by Serre in his 1997 paper that I mentioned. Generally, these are in papers of other people working in this area. These are usually called cyclically non-backtracking walks, CNBWs. We'll just call it circuit using the notation of Serre. And cycle is very nice. A cycle does not have any repeated edges. Okay, in fact, it does not have any repeated vertices. So these are some special types of walks that we are interested in because eigenvalues of D-regular graphs, their traces, the sums of eigenvalues can be expressed in terms of these, the number of these types of walks. Okay, so let me briefly introduce the families that we are interested in, namely the eigenvalues of regular graphs. So let us take two positive integers, m and d. Let us take d to be greater than or equal to 3. And we consider the collection of all d-regular, simple, undirected graphs on m vertices. Okay, because the number of vertices is finite. Obviously, this collection is also finite. And we label, so corresponding to any graph, we can talk about its adjacency matrix. So let us say we label our vertices in terms of V1, V2 up till V sub n. The adjacency matrix of a graph is defined in such a way, so it has entries 0 or 1, and the ijth entry is 1 if there is an edge Vi comma Vj in this graph and it is 0 otherwise. So if there is an edge joining Vi to Vj, then the ijth entry is 1 and it is 0 otherwise. it is easy to see in our context, we are taking undirected graphs, that A is symmetric and therefore has only real eigenvalues. And these eigenvalues are called the eigenvalues of your graph X. So let us see some particular types of eigenvalues. If you have a D-regular graph, it is easy to see that D itself is an eigenvalue of your graph. Okay, so this is called the trivial eigenvalue of your graph. And one can also see that any eigenvalue of your graph would lie in the interval minus D to D. Okay. Now, what we do is we take away those eigenvalues whose absolute value is D. So if minus D is an eigenvalue of the graph, which happens if the graph is what is called a bipartite graph, then minus D is also an eigenvalue. So we are not really considering those. So take away the trivial eigenvalues and consider the non-trivial eigenvalues of a graph. So let us characterize lambda of X to mean the maximum possible size of the non-trivial eigenvalues of your graph X. And we want to know how lambda of X behaves. So we want to basically understand the location of the non-trivial eigenvalues of X. So there is a very beautiful theorem in graph theory, which tells you the following. It says that the probability of a non-trivial eigenvalue to be greater than 2 times square root of D minus 1 is very, very little. It goes to 0. Okay. So the number of graphs for which lambda of X, which is the maximum of the non-trivial eigenvalues, is greater than 2 times square root of D minus 1 plus epsilon is little o of the total number of graphs, D-regular graphs on M vertices. So if you choose a random graph from your collection G of M comma D, the probability that its non-trivial eigenvalues jump outside the interval minus 2 square root of D minus 1 to 2 square root of D minus 1 is very, very small. It goes to 0. Now you can, just as we normalized the Hecker operators, we can normalize the family of eigenvalues of the adjacency matrix. Okay, so in that case, what we have is that with respect to this normalized normalized adjacency matrix, the probability of a non-trivial eigenvalue going beyond minus 2 to 2 goes to 0 as the size of your graphs grows. Okay, so the probability that lambda of X is greater than 2 plus epsilon goes to 0. So this is not quite the analog of the Ramanujan-Deligne theorem. In the context of eigenvalues of Hecker operators, we just knew that all the eigenvalues lie in the interval minus 2 to 2. Here, what we know is that as the size of your graphs grows larger and larger, the probability of an eigenvalue going beyond minus 2 to 2 is very, very small. But there are certain eigenvalues, there could be, it's just that their numbers are negligible. So now, whatever we did for distribution of zeta zeros and distribution of eigenvalues of Hecker operators can be repeated in the context of distribution of eigenvalues of regular graphs. So let us choose a sequence of graphs, okay, where X sub M lies in your set of D-regular graphs on M vertices. The question is, how are the families of these normalized eigenvalues distributed in this particular interval as M goes to infinity? Here I'm fixing D. Okay, so if D is fixed and our M goes to infinity, the families G of M comma D still keep growing. The question is, how are the families of eigenvalues distributed? So what we have done is, for each M, we have chosen a specific graph in G of M comma D. The other question one can ask is, what happens if you let D also to grow along with M? Then how are the families of A of X sub M distributed as m goes to infinity, and these this distribution can be studied in terms of the corresponding counting functions. So here this is n sub I of x sub m. So it's the number of eigenvalues of x sub m, the normalized eigenvalues lying in the interval I. Okay, so how do these counting functions behave? Okay, and in deep inside this theory, you can also express these n sub I of xm's in terms of sums of random variables. But we don't go into those details right now, but I want to tell you some major theorems in this direction. So a famous 1980 theorem of Brandon McKay tells us that if you are choosing your sequence of graphs in such a way that the number of cycles of length m is little o of m as m goes to infinity, then there is a distribution measure for these counting functions, for these eigenvalues. And this distribution function is in fact quite similar to the p-adic Planteral measure. In fact, if your d is p plus 1, we exactly recover the p-adic Planteral measure for eigenvalues of the fixed Hecke operator t sub p. So here our parameter of degree seems to behave like the parameter p when we were talking about eigenvalues of Hecke operators. Okay. So in his 1997 paper, Serre was actually concerned with general equidistribution principles, which he applied to eigenvalues of Hecke operators, as well as eigenvalues of regular graphs. And he also gives a criterion which is necessary and sufficient for an equidistribution measure to exist for a family of regular graphs. So let me just introduce quickly some questions about eigenvalue statistics. So given a function f, let's take a real valued function defined on R, we may define the following random variable on the collection or on the set of all d regular graphs on m vertices. Do it as follows. So for a specific graph x sub m, let b sub f of x sub m denote the sum of the values of your function f over all the lambdas lying in your family of non-trivial eigenvalues of x sub m. So this can be viewed as a random variable on this family G of m comma d. And a theorem of Dumitriu and Paul tells us that this the expected value of this b sub f is asymptotic to the integral of your function f with respect to the same Sato-Tate measure, which we had got for sums of our random variables t sub p in modular cusp forms. And so, however, for this theorem to hold, Dumitriu and Paul require the degrees to grow quite, the number of vertices to grow quite fast as compared to the degrees. So even if your D is growing along with M, eventually M should be greater than any power of D. This is what this growth condition here is telling us. So under these conditions, they know asymptotics about the expected value of B sub F. And so now in central, we can ask questions about variance and central limit theorems. So this is a result of Tobias Johnson in 2015. For certain types of test functions, he doesn't take the kind of test functions that we were taking. He doesn't take the characteristic function, for example. But for some types of test functions, which can be expressed as sums of the Chebyshev polynomials, and the ANs are suitably controlled, okay, if your degree D goes to infinity under this very, very strong condition, okay, then you have asymptotics for the variance of this random variable B sub F, and you also have asymptotics for higher moments of your B sub F. Okay, so these also converge to the Rth power moments of the Gaussian distribution. So there is a lot of underlying similarity with the eigenvalues of Hecke operators. And in ongoing joint work with my colleague here, Momanty Poddar, we are looking at these central limit theorems and trying to see if we can take other types of test functions where more flexible growth conditions can also work. This growth condition is quite horrible. So we want to see if we can improve this. Okay. And what, for example, some types of test functions that we have looked at, and this is ongoing work, is functions of this form. So these are also combinations of your Chebyshev polynomial, and U of n have some kind of a sub-exponential decay. Okay, so far what we have is results about expected value. So here we have that under these better growth conditions, which are much better than what Johnson had considered, we know that the expected value is asymptotic to the integral of H sub L with respect to the Sarto-Tate measure. And we also have some results about variance and central limit theorems for some other types of test functions. But I will, since this work has not been written up completely, it's ongoing, maybe I will leave it at that with just some comments about just the expected value. We can make this asymptotic effective with effective error terms. So we have an error term of the following form. And then we have to look at different types of analogs of the central limit theorem here. Okay, so some concluding remarks. The families, so we looked at 3 different families today, the families of angles corresponding to zeta zeros of curves, families of Hecke eigenvalues, and families of eigenvalues of regular graphs. Now, in the case of zeta zeros of curves, the families that we considered were uniformly distributed in the unit interval. So the counting function, we were able to actually write as sums of seemingly independent but identically distributed random variables. In the other statistics that we see, this we write our counting functions as sums of random variables which look independent but are not identically distributed. So there are more general central limit theorems known for them had they been independent, but we don't know. We cannot apply those central limit theorems directly, but we can use them to predict central limit theorems. So Serre, I already mentioned to you that Serre had presented some general principles of equidistribution. So what he did was he wrote down a very nice theorem which can be viewed as a recipe to derive equidistribution for different types of families, and he applies his general theorem to the families of Hecke eigenvalues as well as eigenvalues of random regular graphs. So now the question is, this is a question to which I do not have an answer yet, but something we can all think about. Is there a general theorem from which all of the above CLTs can be derived as special examples? Okay, so I stop my talk on this note. I would like to refer certain papers and nice articles on the topics that we have seen in our 2 lectures. So first is, of course, Sieving and the Erdős-Katz theorem. It's an article in this volume called Equidistribution in Number Theory, brought out by the NATO Science series. It's also available on the web pages of Granville and Soundararajan. So this is a direct proof of Erdős-Katz theorem using explicit number theory. This is what we had reviewed in our previous lecture. Okay, then I mentioned these notes of Chantal David. So curves and zeta functions over finite fields. These are notes from some lectures that she gave at Arizona Winter School in 2014. With respect to the eigenvalues of Hecke operators, I'd like to refer to the paper of Serre. This is the fundamental paper in this field. This paper is in French, so if you don't want to read in French, you can read my paper with Ramurthy, where essentially we translate all of Serre's paper and also give more general principles to derive effective error estimates in equidistribution theorem. Then in my paper with Neha Prabhu, we talk about the central limit theorems. So this is a reference to that. There was another paper that we wrote with Stefan Bayer, where we talked about central limit theorems for more general smooth random variables. And the work of Toby is also available. It appeared in the Electronic Journal of Combinatorics in 2015. Toby does not use the method of moments. He uses his paper is a little difficult to read if you are not very familiar with probability. So Momanthi and I are actually finishing our draft of the paper, and I'll be happy to share it with the organizers once it's ready, hopefully by the end of this month, and you are welcome to share it on your webpage. So I stop on this note. Thank you. Sorry, I went over time today.
No problem. Thank you so much for a very nice talk,
Thank you.
Kaneenika. Are there any questions?
There are some comments in the chat
Okay, let me
by
just.
Professor Ajit Iqbal Singh.
Okay. So result of Preston, degree n at nth stage may not be achievable. So Professor Singh, is your question in the context of the test functions that Tobias Johnson was taking, or I didn't quite understand.
You see, you kept saying a polynomial Pn of degree n.
Yeah,
But
yeah.
to achieve such an approximation, you know, the degrees may be different. And there is a paper by Preston and a student that degree n approximation is not achievable. Now you can create an artificial sequence from any sequence for which degree n of the nth polynomial is not n, but the natural approximations may not have exact degree n for the polynomial at nth stage.
I see. Okay.
Okay,
So,
after you have a sequence, then you can choose a subsequence and then maybe change the degree by adding an artificial factor and then have that degree. But the natural approximations may not have degree n at the nth stage.
I see. Okay, thank you. I will look
Thank
at
you.
it.
And a wonderful talk. Thank you very much.
Thank you. So Sneha has a question.
Another thing that I said last time also, there are central limit theorem in quantum setup, and Robin Hudson was a pioneer in the 70s also, and his student.
Okay.
Thank you.
Yeah, thank you.
Yeah, Sneha.
Yeah. Hi, Kaneenika.
Hi.
Very nice talk.
Thank you.
So I had a question related to Serre's result. So Serre's result, he does give a existence about the measure, right? With respect to so the different measures with respect to which the sequence would be equidistributed. So like, does he also give a recipe to find what the measure would be, like for different scenarios, or for each of these cases you already know what the measure is, right? Or
yeah, this is a great question. So Serre gives us sufficient conditions for a distribution measure to exist. And in the families that he was considering, we could see from the calculations what the measures would be. But he does not give an exact recipe to derive those measures. But that recipe is also known by the work of Wiener and Schoenberg. There is a known recipe. So in my paper with Ramurthy, we review this theorem of Wiener and Schoenberg, where we know once you know that your families satisfy certain types of conditions, then how do you actually derive the distribution measure, and how do you derive effective versions of your equidistribution theorem. So that has been done more in my paper with Ramurthy. Yeah.
Oh, okay.
That answers.
So then, like with that, would you also be able to derive this measure for regular graphs, for example?
Yes.
Okay.
For these, actually here the measures are known.
Okay.
Yeah. Which are actually remarkably similar to the p-adic Planteral.
Right.
In fact, it's exactly the same if your d were equal to p plus 1.
Okay.
Yeah.
Okay. Great. Yeah. Very nice. Thank you.
Any other questions?
Hi, I had a question.
Hi.
Nice talk.
Thank you.
So this is kind of general, but like with these CLTs, we are generally referring to Gaussian type distributions. Is it like the normal distribution?
I chose families which satisfy but there could be other types of distributions.
Okay. So those are also, when we say central limit theorems, it could also mean like Poisson distribution or something of
So,
that sort.
okay, no, as far as I'm aware, central limit theorems usually refer to distributions which converge to the Gaussian distribution.
I see.
But there are different types of families where you can consider random variables and sums which converge to different types of, say Bernoulli random variables or Poissonian. So in her notes, Chantal describes many of those families as well.
Okay. Somehow it seems like the Gaussian pops up more often or is more natural in some way, I guess.
Yeah, somehow in a lot of the counting functions for
I
Zeta
see.
zeros, the Gaussian
Comes
showed
up.
up. Yeah.
Okay.
Yeah.
Okay. And I had one question about this zeta function of the curves. So you initially defined it as an exponential of a series, right?
Yeah.
And
Yes.
yeah. So, and then I think, let me see.
Yeah, because of your function field arithmetic, this turns out to be actually a rational function.
Yeah, so this part, is it like easy to see or is it non-trivial? Because I was just, is it some big thing to go from that first statement to the second statement, or can one see it?
I don't remember the exact details, but it is not very difficult.
I see. Because it looks funny because it's an exponential of a infinite series, but then it becomes this this nice rational function. So I was thinking, is it some non-trivial result?
No, it's not.
Okay.
Yeah.
I see. Yeah. Okay.
Any other questions? Okay, if not, let's unmute ourselves and thank Kaneenika for these wonderful lectures.
Thank you.
I hope this will set up a precedent for other such courses by other people. So we look forward to it.
Including by Atul Dikshit.